In October of 1927, someone took a photograph in Brussels. 29 people, most of them in dark suits, chairs arranged in 3 rows, a black and white shot, the kind of unremarkable conference photo you find by the thousands in any archive. But this one is different. 17 of those 29 people had already received, or would go on to receive, the Nobel Prize. Planck, Einstein, Bohr, Heisenberg, Schrödinger, Pauli, de Broglie, Dirac, Marie Curie. The highest concentration of raw intellectual firepower per square foot in the history of our species. They had gathered in Brussels to answer a single question. Not how quantum mechanics works, they had already figured that out, but what it means, what it says about the nature of reality itself. And here is what was happening just outside the frame of that photograph. Every morning, Einstein came down to breakfast with a new thought experiment. A carefully constructed trap, designed to show that quantum theory contradicted common sense and physical reality. Every evening, Niels Bohr found a way out. The next morning, Einstein came back with a new one. Bohr found another way out. They did this year after year, conference after conference, letter after letter, until one of the greatest minds in the history of science died in Princeton in 1955. Unconvinced, unpersuaded. And then, 9 years after his death, an Irish physicist named John Bell wrote a few pages of equations and showed that the argument between Einstein and Bohr was not a philosophical dispute. It was a testable prediction about the nature of reality. The test was done. Bohr won. Einstein was wrong. And here is the strangest part of all this. The very questions that Einstein raised because he hated quantum theory led directly to quantum computers, quantum cryptography, and the technologies that power the world right now. Even in losing, he was pointing in the right direction. Right now, as you listen to this, the screen of whatever device you are holding runs on transistors. Billions of them, each one a tiny switch. And every single one of them operates according to rules that say an electron can be in several places at once, can pass through a wall it should not physically be able to cross, and has no definite position at all, until you look. Nobody told you that when you first picked up a phone, which is strange, because this is not an abstraction buried in a physics journal somewhere. This is literally how the device in your pocket works. So how did we get here? How did a group of people with pencils and chalkboards discover that reality at its deepest level works nothing like it looks? Why did the discovery contradict common sense so completely that some of the people who made it refused to believe it themselves? Why did the 2 greatest physicists of the 20th century argue about it until the end of their lives? And why is that argument still not entirely closed? What happens to an electron when nobody is looking at it? Why does quantum mechanics predict the behavior of particles to 12 decimal places of accuracy and still cannot answer the question of what any of it means? That is what we are going to talk about tonight, slowly, from the very beginning, without rushing anywhere it matters to linger. If you drift off somewhere along the way, that is perfectly fine. Some things are easier to absorb on the edge of sleep, when your mind stops demanding that everything fit into the familiar picture. Because the familiar picture does not work here, and the sooner you let go of it, the easier the rest becomes. To understand why the quantum revolution was so staggering, you need to start with what physics looked like in the 1890s. It was in a rare state of triumph, close to smugness, and there were reasons for that. Isaac Newton, back in the 1600s, had written down equations that described the motion of everything you could see or touch. If you knew where an object was, how fast it was moving, and what forces were acting on it, Newton's equations would tell you exactly where it would be at any point in the future, with absolute precision, forever. The universe as a clockwork mechanism, endlessly complicated, but completely predictable. Then, in the 1860s, a Scottish physicist named James Clerk Maxwell took electricity and magnetism, two phenomena that people had studied separately, and showed they were two expressions of the same thing. His four equations described electromagnetic waves traveling through space. And when he calculated the speed of those waves, it came out to be exactly the same as the speed of light. Light is an electromagnetic wave, just a ripple in a field, spreading through space. By the 1890s, thermodynamics was worked out and systematized. The periodic table was filling in. Optics explained prisms and lenses. Chemists understood how substances combined. Lord Kelvin, one of the leading physicists in Britain, supposedly told a room of students around 1900 that there was nothing new to discover in physics anymore, only more precise measurements to be made. Historians argue about the exact wording, but the mood was real. Physics looked like a finished building. All that remained was polishing the details. There were two small anomalies, two experimental oddities that did not fit the overall picture. Kelvin called them two small clouds on the otherwise clear horizon of physics. He figured they were temporary. Someone would sort them out within a few years. One of those clouds had to do with how hot objects glow. Take a piece of metal and heat it, and it starts to glow. First a dark red, then orange, then at high temperatures, yellow and white. The color of the glow depends on the temperature. Any blacksmith knows this. By the 1890s, physicists had measured this carefully. Beautiful curves showing how much energy was radiated at each wavelength for each temperature. Fine. Now try to explain it. They took Maxwell's equations and the laws of thermodynamics and tried to predict the shape of that curve. The calculations were honest and careful. The result was a disaster. According to classical theory, as the wavelength got shorter, moving from red light toward violet, toward ultraviolet, the power radiated should keep climbing without limit. A warm object should emit an infinite amount of energy at short wavelengths. That would mean any warm mug sitting on a table near you would be a source of lethal ultraviolet radiation. Opening an oven door would mean exposure to deadly rays. Your own body, which is warmer than the air around it, should be killing you right now. Obviously, none of that was happening. The failure got a name: the ultraviolet catastrophe. The theory predicted infinity, where the experiment showed a smooth curve that peaked and then fell back toward zero. Something fundamental in classical physics was wrong, and nobody knew what. This is where the first figure in our story walks in. In 1900, a 42-year-old professor of theoretical physics in Berlin was working on this exact problem. His name was Max Planck. Methodical, careful, deeply committed to the classical worldview. One of his professors had once advised the young Planck against going into physics, saying there was nothing left to discover. Planck reportedly said he did not want to discover anything new. He just wanted to better understand what was already known. History made that answer very ironic very quickly. Planck worked through the black body radiation problem. He tried approach after approach. Eventually, he found a formula that matched the experimental data perfectly. At all wavelengths, at all temperatures, with no catastrophe at the ultraviolet end. The problem was that for this formula to make physical sense, he had to accept something strange.
He assumed that energy could not be transferred in arbitrary amounts, only in discrete chunks, which he called quanta, from the Latin word for how much. If you want to transfer energy at a particular frequency, you can transfer 1 quantum, 2, 3, 1,000,000, but not 1.5, and not 2.25. Only whole numbers of quanta. The size of each quantum was set by the frequency. E equals h times nu, where nu is the frequency and h is a new, tiny constant that Planck introduced specifically for this purpose. We now call it Planck's constant. It is unimaginably small, roughly 6.626 times 10 to the negative 34th joule seconds. What does this change?
For high-frequency ultraviolet radiation, each quantum is enormous. At ordinary temperatures, an oscillator simply does not have enough energy to emit even one of those quanta. It cannot afford the price of admission, so it emits nothing. The ultraviolet catastrophe disappears. The formula worked. It explained everything. Planck himself did not believe what he had written. He considered quantization a mathematical trick, a forced workaround that some future physicist would replace with a proper, physically sensible explanation. He later wrote that it had been an act of desperation, that he had been willing to sacrifice anything just to get an answer. On the 14th of December 1900, he presented the results to the German Physical Society in Berlin. That date is now considered the birthday of quantum physics, even though the man responsible had no idea what he had started. A door into a new world had opened, and the next person through it had no intention of closing it. Planck thought quantization was a temporary fix, that someone would soon come along and explain everything properly, without those discrete chunks of energy. He could not have known that the next physicist to pick up his idea would not correct it. He would take it literally, and in doing so, set off a chain of events that would never stop. The year 1905 is what historians of physics call Einstein's annus mirabilis, his miracle year. In the space of 12 months, Albert Einstein, a 26-year-old third-class technical expert at the Swiss Federal Patent Office in Bern, published 4 papers. Any one of them would have been enough for a full scientific career. One was on Brownian motion, proving the reality of atoms. One was the special theory of relativity, overturning everything physics believed about space and time. One introduced the equation E equals mc squared. And then there was a fourth, the one Einstein himself would later call genuinely revolutionary. The one that won him the Nobel Prize in 1921. Not for relativity, as most people assume, for this 4th paper. It was called On a Heuristic Point of View Concerning the Production and Transformation of Light. In it, Einstein took what Planck had considered a mathematical trick and said, "No, this is not a trick. This is reality." Planck had assumed that the oscillators in the walls of a hot body absorbed and emitted energy in discrete chunks. But the electromagnetic field itself, light itself, was still, in Planck's view, continuous. The discreteness was only in the exchange. Einstein went one step further. What if light itself consists of discrete packets? What if a photon is not a convenient unit of bookkeeping, but an actual separate particle traveling through space? This explained another experimental anomaly that had puzzled everyone for years: the photoelectric effect. When you shine light on a metal surface, electrons fly out of it. That had been known since 1887. Makes sense on the face of it. Light carries energy. Energy knocks out electrons. But the details did not add up. By wave logic, the brighter the light, the more energy it carries, the faster the electrons should fly out. That is not what happened. Brightness only affected how many electrons came out, not how fast each one was moving. The speed depended on the color, the frequency of the light. Worse, red light knocked out no electrons at all, no matter how bright. None. But the moment you switched to blue light, even a very faint beam knocked electrons out immediately. Wave theory had no explanation for this. Einstein explained it in a single paragraph. If light is a stream of photons, and each photon carries energy equal to its frequency multiplied by Planck's constant, then everything fits. A red photon carries too little energy to knock out an electron. No number of red photons helps, because each one interacts with an electron one-on-one. A blue photon carries enough, and one is all it takes. No mystery. But here is what this did to physics as a whole. Maxwell had conclusively shown that light is a wave. Diffraction, interference, polarization, all of them wave phenomena, confirmed thousands of times. Light is a wave. Einstein had just shown that light is a particle, also proven. Both statements are true, both are confirmed by independent experiments, and they contradict each other at the level of basic definitions. A wave is a continuous distribution in space. A particle is a localized object. This became known as wave-particle duality, and it is not a metaphor, not a consequence of imperfect instruments. It is a fundamental property of light, and, as it would turn out, of all matter. Niels Bohr would later say, "There is no point asking what light really is. Light shows you one face or the other depending on how you look at it. Trying to picture it in reality is trying to apply to the quantum world categories that we developed from our experience with large, slow objects. Those categories simply do not apply." Einstein disagreed, and that disagreement became the seed of their lifelong argument. But in 1905, the argument is still years away. For now, physics has another puzzle that classical theory cannot solve. And in Manchester, an experimenter is about to fire tiny particles at a sheet of gold foil. And what he finds will push physics toward one more crisis that only the quantum can resolve. Light turned out to be both a wave and a particle. That paradox was uncomfortable, but you could set it aside if you tried hard enough. The next blow came from inside matter itself, and there was no looking away from it. Ernest Rutherford was a New Zealander with a loud voice and a reputation for always getting a result. Working in Manchester, he set up an experiment in 1909 that looked simple on the surface. His graduate students, Geiger and Marsden, aimed a beam of alpha particles, tiny helium nuclei, at an extremely thin sheet of gold foil. On the far side stood a screen of zinc sulfide that flashed whenever a particle hit it. They sat in a darkened room for hours counting flashes, recording the angle at which each particle was deflected. The accepted model of the atom at the time was J.J. Thomson's. In that model, the atom looked something like a plum pudding, a soft, diffuse ball of positive charge with electrons embedded inside it. Alpha particles were expected to pass through the foil with only slight deflection, the way a bullet passes through fog. Most of them did exactly that, but roughly 1 in 8,000 bounced almost straight backward, close to 180 degrees, as if it had hit something tiny, dense, and hard. Rutherford later wrote that it was like firing an artillery shell at a sheet of tissue paper and having it come back and hit you. He spent months rechecking the results, unwilling to believe them. The only possible explanation: all of the positive charge and nearly all of the mass of the atom had to be concentrated in a fantastically tiny central nucleus. So tiny that if you scaled an atom up to the size of a football stadium, the nucleus would be a marble sitting at the 50-yard line. Everything else, all the space where the electrons were supposed to live, was essentially empty. The atom is almost entirely nothing. That is beautiful in its own right, and it created an immediate, catastrophic problem.
If an electron is orbiting a positively charged nucleus, it is undergoing accelerated motion, constantly changing direction along a curved path. Maxwell's equations are unambiguous on this point. Any accelerating charge emits electromagnetic radiation and loses energy as it does. An electron should lose energy continuously and spiral inward toward the nucleus. The calculations said this would take roughly 10 to the negative 11th seconds, which meant Rutherford's atom should not exist. All atoms everywhere should have collapsed almost instantly after forming. They had not collapsed. You can feel that right now in the solidity of whatever surface you are resting on. Something was preventing electrons from falling into the nucleus, something that classical physics had no way to explain. In 1912, a young Dane named Niels Bohr arrived in Manchester to work with Rutherford. Bohr was famously slow and deliberate in speech, so careful in his formulations that listeners sometimes lost track of what he had just said. But when he finally said something, it tended to be right. Faced with the stability problem, Bohr did something philosophically bold. He did not try to solve it within classical physics. He said, "Classical physics simply does not apply here." And he introduced new rules. Bohr's rules, published in 1913, stated that electrons could only exist on certain specific orbits without radiating energy. When an electron jumped from one orbit to another, it absorbed or emitted exactly one photon, with energy equal to the difference between the two levels. This predicted the spectrum of hydrogen, the specific colored lines that hydrogen emits when you heat it. A Swiss math teacher named Balmer had found a formula for those lines back in 1885, but nobody understood why it worked. Bohr's model explained all of them, with an accuracy that could not be a coincidence. Einstein, when he heard about it, said it was one of the greatest discoveries ever made. But Bohr himself knew perfectly well that his model was a crutch. It worked for hydrogen and fell apart for more complex atoms. And most importantly, it gave rules without explanation. Why these orbits? Where did the discreteness come from? The answer took another 10 years, and it came from an entirely unexpected direction. Bohr had temporarily saved the atom from collapse by introducing rules with no foundation under them. Explaining those rules required a genuinely new idea, one so strange that its author was not entirely sure he had not lost his mind. Louis de Broglie came from an old French aristocratic family. He started out studying history at the Sorbonne and planned a diplomatic career. But his older brother Maurice was a physicist working with X-rays, and their conversations at family dinners gradually pulled Louis towards science. He left history and switched to physics. In 1923, de Broglie was working on his doctoral thesis, and he was turning over a question that even he was not sure was a serious one. Einstein had shown that light, which everyone had considered a wave, behaves like a particle. Photons are real things, so what if the principle worked in both directions? What if an electron, which everyone considered a particle, also behaves like a wave? De Broglie wrote down a formula, not just an idea, but a specific mathematical prediction. The wavelength associated with any particle equals Planck's constant divided by the momentum of that particle. Lambda equals h over p. His doctoral committee was not sure what to make of it. One member sent the paper to Einstein for a second opinion. Einstein wrote back that de Broglie had lifted a corner of the great veil. The thesis was accepted. In 1927, the prediction was tested. Clinton Davison and Lester Germer at Bell Labs in New York aimed a beam of electrons at a nickel crystal. The atoms of the crystal were arranged in a regular lattice, a perfect diffraction grating for waves.
The electrons produced a clear diffraction pattern, the kind of pattern that only waves make when they bend around obstacles and interfere with each other. The same kind you get when you scatter X-rays off a crystal. De Broglie's prediction was confirmed. Independently, George Thomson in Aberdeen showed the same thing. George Thomson was the son of J.J. Thomson, who had discovered the electron as a particle. The father found the electron was a particle and won the Nobel Prize. The son showed the electron was a wave and won the Nobel Prize too. Both were right. This explained Bohr's mystery. If the electron in an atom is a wave, then that wave has to fit around the nucleus a whole number of times. Otherwise, it creates destructive interference. The wave cancels itself out on each pass. Only those orbits where the wavelength fits perfectly around the circumference are stable. Those are exactly the orbits Bohr had postulated, without knowing why. His rules had been wave optics all along, written in the language of pre-quantum physics. By 1925, the picture looked like this. Light is both wave and particle. Electrons are both wave and particle. Atoms are stable because of the wave nature of their electrons. What was needed now was an equation describing how those waves behave, how they evolve over time. That equation appeared in 1925 and 1926, twice, written by two different people in two different ways. Matter turned out to be a wave. Now someone needed an equation for that wave. It arrived in 1925 and 1926, twice, from opposite ends of Europe. One version was written on a rocky island in the North Sea by a man with terrible hay fever. The other was written during a Christmas vacation in the Alps with a woman whose name history never recorded. Summer of 1925. Werner Heisenberg is 23 years old. He is working as an assistant to Max Born in Göttingen and suffering through a brutal bout of hay fever. He asks for a week's leave and travels to Helgoland, a tiny rocky island in the North Sea, almost without vegetation and therefore almost without pollen. On the island, he works through the night on a problem that has been bothering him for months. Heisenberg is convinced that quantum theory needs to be built only from things you can actually observe. You cannot see the orbit of an electron. You cannot see its trajectory. What you can see are spectral lines, specific frequencies and intensities of emitted light. So why not build a theory entirely out of those numbers? He constructs mathematical tables, arrays of numbers describing transitions between atomic states. When he multiplies these tables together, he notices something troubling. The result depends on the order of multiplication. A times B does not equal B times A. In ordinary arithmetic, 3 times 5 equals 5 times 3. Here it does not. It is strange enough that Heisenberg checks the calculations several times over. Around 3 in the morning, he satisfies himself that the math is right. He is too excited to sleep. He walks to the edge of the island and watches the sun come up over the North Sea. When he returns to Göttingen and shows the results to Max Born, Born immediately recognizes the mathematical structure. This is matrix algebra, a branch of mathematics developed in the mid-1800s, which Heisenberg had never studied. The non-commutativity, A times B not equaling B times A, is a fundamental property of matrices. Born, together with a physicist named Pascual Jordan, helped organize everything into a system. This became matrix mechanics, the first complete quantum theory. It worked. Its predictions matched experiments, but it was agonizingly difficult to work with. Dense abstraction without a single physical image to hold on to. A few months later, December of 1925, a chalet in Arosa in the Swiss Alps. Erwin Schrödinger, 38 years old, Austrian, had brought a woman with him on a Christmas vacation, not his wife. The details of Schrödinger's personal life followed rules that did not line up especially well with the conventions of his era. Over a few weeks in the mountains, he wrote an equation that now bears his name. Schrödinger started from de Broglie. If an electron is a wave, there should be a wave equation. Something like Maxwell's equations for electromagnetic waves. He found it. The Schrödinger equation describes how a mathematical object called the wave function, denoted by the Greek letter psi, evolves over time. This is not a coordinate or a velocity or any familiar physical quantity. It is a function defined at every point in space, changing over time. In form, it was recognizable to physicists as a partial differential equation of the same kind used to describe vibrating strings or heat flow. It was immensely easier to work with than Heisenberg's matrices. Schrödinger initially thought the wave function was a real physical wave, that the electron was literally spread out across the region described by psi. Then Max Born stepped in. Born pointed out that the square of the magnitude of the wave function at a given point is the probability of finding the particle at that point when you measure it. The wave function is not the electron itself. It is a description of the likelihood of finding the electron in each location. Before measurement, the electron has no definite position. There is only a probability distribution. When you measure, the wave function collapses from a spread-out cloud of probabilities to a single, specific point. This was a fundamentally new kind of claim. For the first time in the history of physics, a fundamental theory was saying, the world is probabilistic, not because we are missing information, but because probability is a basic feature of reality at the quantum level. Before measurement, there is no fact about where the electron is. Not, we do not know where it is. There is simply no place where it was before we looked. Later, in 1926, Schrödinger proved mathematically that his wave mechanics and Heisenberg's matrix mechanics contained identical physical content, just written in different languages. Like the same sentence in German and in English. Quantum mechanics had become a unified theory. It worked flawlessly. Its predictions matched experiments. But what it meant physically, nobody agreed. And that disagreement became the reason for a meeting in Brussels. Quantum mechanics now had an equation, brilliant and precise, but nobody could agree on what it was describing. In 1927, the physicists gathered in Brussels. And that is where Einstein and Bohr began an argument that would last until one of them died. The Fifth Solvay Conference opened on the 24th of October, 1927, in Brussels. The theme was electrons and photons, which really meant, what does quantum mechanics say about physical reality? By that point, the math was settled. The interpretation was not. Bohr had by then developed a position that became known as the Copenhagen interpretation. Its key claims were these. Quantum mechanics is a complete description of reality. There is nothing deeper underneath it. No hidden variables that would explain where the electron really is. Before measurement, a particle has no definite values for observable quantities. There is no meaningful sense in which an electron has a position before that position is measured. Measurement does not reveal a pre-existing reality. It creates one. Einstein could not accept this, and his refusal was not stubbornness or eccentricity. It was a deeply held philosophical position. He believed in objective reality. Things have properties whether or not anyone is observing them. The moon exists when nobody is looking. An electron has a definite position. We just do not always know it. Quantum mechanics, in his view, described our ignorance, not reality itself. God does not play dice with the universe, he said. The phrase became his calling card. Einstein, stop telling God what to do, Bohr replied. The morning ritual at the conference became the stuff of legend. Every morning over breakfast, Einstein would lay out a new thought experiment, a carefully constructed trap designed to reveal an internal contradiction in quantum theory. All day Bohr would pace, mutter, explain things to colleagues, fill napkins with diagrams. By evening, he would announce a way out. The next morning, Einstein came back with a new one. Bohr found a way out every time. Einstein's core argument was this: the Heisenberg uncertainty principle is a limitation on our knowledge, not a property of reality itself. If we knew the initial conditions precisely enough, we could predict the outcome of any measurement with certainty. Quantum uncertainty is a consequence of our epistemic limits, not a fundamental feature of the universe.
Bohr replied, "The uncertainty principle is built into the mathematics of quantum mechanics. It has nothing to do with the quality of our instruments. It is a property of quantum objects themselves." Neither man convinced the other. At the next Solvay conference in 1930, Einstein arrived with a particularly sophisticated argument that historians call Einstein's box. He described a thought experiment. Take a box filled with radiation. The box has a shutter controlled by a clock. The shutter opens for a fraction of a second and lets out exactly one photon. Weigh the box before and after. Using Einstein's own formula, E equals mc squared, the change in mass tells you the exact energy of the emitted photon. And you also know the exact moment it left. So you know both energy and time, which would violate the time-energy version of the uncertainty relation. That evening, Bohr looked rattled. Several participants noted it. He clearly had not found an answer immediately, but by morning he had one. When the box loses mass as the photon escapes, it shifts slightly upward in the gravitational field. Einstein's own general theory of relativity says that clocks higher in a gravitational field run faster. That shift in the box's position introduces an uncertainty in the clock reading. When you work through the numbers carefully, that uncertainty turns out to be exactly what Heisenberg's principle requires. Einstein had tried to break quantum theory. His own theory of gravity had defended it. He conceded the point in that specific argument, but he did not give up overall. He simply changed tactics. He stopped trying to show that quantum mechanics was internally inconsistent. Now he wanted to show that it was incomplete. Einstein stopped attacking the logic of quantum mechanics. Instead, he wanted to prove that a deeper reality must lie underneath it. In 1935, he published a paper that, without meaning to, opened the door to the technologies of the 21st century. In the spring of 1935, Einstein and his colleagues Boris Podolsky and Nathan Rosen published a paper with a dry academic title: "Can the quantum mechanical description of physical reality be considered complete?" The answer they were arguing for was no. Their argument, which became known as the EPR paradox, was elegant and, on first reading, hard to counter. Imagine two electrons emitted from a single source in opposite directions, in a combined state where their total spin is zero. Spin is a quantum property of a particle with two possible values, up and down. If the total spin is zero, then if one is up, the other must be down. Let them fly apart, to opposite ends of the Earth if you like. According to quantum mechanics, until either one is measured, neither has a definite spin. Both are in superposition, up and down at the same time. We measure the first electron and find its spin is up. At that instant, instantaneously, the spin of the second electron on the other side of the world becomes down. Instantaneously. Not after a moment, once the signal travels. Instantaneously. Einstein pointed out, this violates special relativity. Nothing travels faster than light. If the second electron learns the result of the first measurement instantly, that is exactly what relativity says cannot happen. His conclusion: the electrons must always have had definite spins from the moment they were emitted. One was always up, the other always down. We just did not know. Quantum mechanics fails to describe these hidden values, and that is its incompleteness. It is like finding a left glove in one package and immediately knowing the other package holds the right glove. There is no instantaneous interaction. The information was there from the start.
Einstein called the quantum version, where the spins are genuinely not defined in advance, spooky action at a distance. The German original is spukhafte Fernwirkung. He considered it absurd. That same year, Schrödinger gave the phenomenon a name: entanglement, from the German Verschränkung. Two electrons emitted from the same source are entangled. Their quantum states are correlated in a way that classical physics cannot account for. Bohr's response to the EPR paper appeared the same year. It was long, occasionally dense, and not everyone found it satisfying. At its core, he was saying, "Your argument assumes particles have properties before measurement, but that is exactly what quantum mechanics denies. You are using as a premise the thing you are trying to prove." Most physicists shrugged and went back to calculating. Debates about interpretation were for philosophers. The math worked, the predictions were accurate. That was enough. Einstein died in Princeton in 1955. Unpersuaded, unconvinced. The argument between Einstein and Bohr seemed purely philosophical, a matter of taste, not of testable fact. Neither position made different experimental predictions. Choosing between them seemed like choosing between worldviews, not between facts. But in 1964, a physicist in Geneva asked a question that turned the whole dispute into an experiment. John Stuart Bell was born in 1928 in Belfast. His father was a horsekeeper, his mother a laundress. He was the only one of his siblings to pursue education past what was required. He studied physics in Belfast, then worked at the Harwell Nuclear Research Centre in England, then at CERN in Geneva. During the day, particle accelerators. In his free time, the question that most of his colleagues dismissed as philosophical. What exactly does the EPR argument prove? Bell formulated a question that nobody before him had stated clearly enough. Is there an experiment whose results would differ depending on whether Einstein or Bohr was right? Einstein's position translated into the language of experiments. Particles carry local hidden variables, specific spin values set from the moment the pair was created. The correlations between measurements are explained by that built-in information. Bohr's position. Particles have no definite values before measurement. The correlations are a non-local quantum connection. It seemed like both positions should produce the same results, because in either case, when you measure one spin as up, the other will be down. Bell showed they would not. If you measure spins at different angles, not just straight up and down, but at various intermediate angles, the statistics of the correlations will differ. For local hidden variables, there is a mathematical upper bound, an inequality, that any such theory must satisfy. Quantum mechanics predicts that this inequality would be violated. The correlations it predicts are stronger than any local model allows, and that is something you can check in a laboratory. The first attempts came in the 1970s. They gave results consistent with quantum mechanics, but the experimental setups had loopholes, technical vulnerabilities that theoretically allowed a local interpretation to explain the results away. The decisive test came in 1981 and 1982. Alain Aspect and his team in Orsay, just outside Paris, ran experiments with entangled pairs of photons, specifically designed to close the main loopholes. The key feature: the angle at which each photon's polarization was measured was chosen randomly after both photons had already left the source. This closed the possibility of any prearrangement. No signal traveling at the speed of light could have told one photon what was being measured at the other detector.
The results were unambiguous. Bell's inequality was violated. The correlations were exactly what quantum mechanics predicted, and they exceeded the maximum possible under any local hidden variable theory. Einstein was wrong. Particles do not carry preset hidden values. Entanglement is a real physical phenomenon. In 2022, the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for precisely these experiments. A few important clarifications about what these results actually prove and what they do not. They prove you cannot simultaneously have locality, nothing acts faster than light, and realism in Einstein's sense. Particles have definite properties before measurement. One of the two has to go. They do not prove that information can be transmitted faster than light. Entanglement does not let you send signals at superluminal speeds. You cannot control which result you get when you measure the first photon. It is random. The correlations only show up when you compare results from both measurements through an ordinary classical channel, which is limited by the speed of light. Entanglement is no less strange for this. Its strangeness just lives in a different place than we thought. Bell turned a philosophical argument into mathematics. Aspect turned the mathematics into an experiment. Einstein's position has been refuted, but Bohr winning does not mean quantum mechanics is understood. And there is one principle that gets misrepresented more than any other result in the field, the one that lies at the heart of all of this strangeness. In 1927, Werner Heisenberg published a principle that has been misrepresented more consistently than almost anything else in physics. The Heisenberg uncertainty principle states that the product of the uncertainties in a particle's position and momentum cannot be less than Planck's constant divided by 4 pi. Delta x times delta p is greater than or equal to h bar over 2. The most common explanation goes like this. To see where an electron is, you have to shine light on it. The photons knock the electron around. The more precisely you want to pin down the position, the shorter the wavelength you need, and the harder the photons hit. That is where the uncertainty and momentum comes from. This explanation is not wrong exactly, but it leads to the wrong conclusion. It creates the impression that uncertainty is a technological limitation, that with better instruments you could know both position and momentum simultaneously. That is not true. The uncertainty is built into the mathematical structure of quantum theory. It follows from the nature of the wave function itself. It will not disappear with improved instruments, not ever. Why? Think about a wave on water. Where does the wave, quote-unquote, exist? A wave is not a point, it is a distribution in space. If you want to pin down a wave's location as precisely as possible, you need a very short wave packet, something like a sharp spike. But that spike is composed of many different wavelengths, a wide range of frequencies. Frequency is connected to momentum, so momentum is uncertain. If you want a wave with a precisely defined frequency, and therefore a precisely defined momentum, you need a pure sine wave running out to infinity in both directions. That kind of wave has no definite position at all. This is a purely mathematical fact about the nature of waves. It follows from Fourier analysis. It has nothing to do with instruments. An electron is a wave. The same constraint applies to it. A state with a sharply defined position is incompatible with a state with a sharply defined momentum. This is a property of the object, not of our competence. Something remarkable follows from the uncertainty principle.
It is precisely why atoms are stable.
If an electron fell into the nucleus, its position would be very precisely defined. It is inside the nucleus, a region roughly 10 to the negative 15th meters across. The uncertainty principle then requires enormous uncertainty in its momentum. Enormous uncertainty in momentum means enormous average kinetic energy. That energy would kick the electron right back out. The balance between attraction to the nucleus and this quantum pressure from the uncertainty principle settles at a specific distance. That distance is the Bohr radius, the characteristic size of a hydrogen atom. Atoms exist because the uncertainty principle prevents electrons from being too precisely located near the nucleus. There is another form of the principle, for energy and time. The shorter the time interval, the less defined the energy of a system during that interval. This means that even in a perfect vacuum, where there are no particles at all, the energy cannot be exactly zero.
Quantum fluctuations are unavoidable. Virtual pairs of particle and antiparticle are constantly appearing and annihilating across all of space. This is measurable. The Casimir effect. Two uncharged metal plates placed very close together in a vacuum attract each other, because the vacuum fluctuations between them are constrained by the geometry, while those outside are not. The imbalance in the pressure of emptiness creates a real, measurable force. The vacuum is not empty. And the uncertainty principle is why. The uncertainty principle is not a limitation on instruments, it is a property of reality. But there is one experiment that shows this more vividly than any explanation. Richard Feynman called it the only mystery of quantum mechanics. Everything else, he said, is a consequence of this one thing. Take a source of particles. Place a barrier in front of it with two slits cut in it. Behind the barrier, a screen that detects whatever hits it.
If the particles are classical balls, each one goes through one slit, and on the screen you get two bright spots. If they are waves, they spread out after the slits and interfere with each other. In some places the waves reinforce, in others they cancel. On the screen you get alternating bright and dark bands. Run this experiment with electrons. Result: interference bands. The pattern of waves. The electron went through both slits at once and interfered with itself. Now turn down the source until electrons are firing one at a time. One, then a pause, then one more. The first electron hits the screen at one point, looks random. The second hits somewhere else. The 100th, the 1000th, the 10,000th. Gradually, a pattern builds. Interference bands, the same ones. A single electron interferes with itself, as if it passed through both slits simultaneously. Now place detectors at the slits.
Quiet, technically sophisticated detectors. They register the fact of an electron passing without physically touching it, or touching it as gently as possible. The interference pattern disappears. The electrons now form two spots. Classical particle behavior. Turn off the detectors, the interference returns. This has been repeated many times with different particles in different labs. The result does not change. And here is the important part. It is not that the detector physically disturbs the electron in a clumsy way. You can make the detector as delicate as you like, the result is the same. It is not the physical interaction that matters. It is whether information about which slit the electron used exists anywhere in the universe. When there is no information about the path, the electron behaves like a wave. The moment that information exists, it behaves like a particle. Reality, apparently, responds to information rather than just to physical disturbance.
There is an even stranger version of this experiment, called the delayed choice quantum eraser. In it, entangled pairs of photons are arranged so that which slit information about the first photon is encoded in its entangled partner. but that partner travels in a different direction, and its measurement happens later, after the first photon has already hit the screen. If the which slit information is preserved when the partner is measured, the first photon shows no interference. If the information is erased, the first photon, which already landed, turns out to have contributed to an interference pattern. The decision to preserve or erase the information is made after the first photon has already registered. This does not allow you to send signals backward in time. The mathematics rules that out completely. But it does mean that you cannot say the photon had a definite, quote-unquote, behavior as it was passing through the slits.
Our intuition that the past is fixed and settled does not apply to the quantum world in the way we are used to thinking. The double-slit experiment shows that reality responds to information, but it raises the question that Bohr and Einstein never settled. What is happening between measurements? Does a quantum object exist when nobody is looking at it? That question split physicists into camps, and it led to the most famous thought experiment in the history of science. Schrödinger himself hated the Copenhagen interpretation. In 1935, to show how absurd he found its implications, he invented a thought experiment. Take a cat. Place it inside a sealed steel chamber. Inside the chamber there is a small amount of radioactive material with a 50-50 chance of decaying within 1 hour. If a Geiger counter detects a decay, a hammer breaks a vial of poison. The cat dies. After 1 hour, is the cat alive or dead? By the Copenhagen interpretation, until the chamber is opened, the radioactive atom is in a superposition of having decayed and not having decayed. So the counter is in superposition. The hammer is in superposition. The cat is in superposition, both alive and dead simultaneously. Schrödinger considered this absurd. The cat is a macroscopic object. It is either alive or dead, regardless of whether anyone is looking. The thought experiment, intended as a critique, became the defining symbol of quantum strangeness. And the question it poses, exactly when does the wave function collapse, and what counts as a measurement, remains one of the central unsolved problems in physics. The measurement problem breaks down like this. The Schrödinger equation describes a continuous deterministic evolution of the wave function. But during measurement, something different happens. The wave function collapses, instantly, to a single definite value, at random. This is not described by the Schrödinger equation. It is an additional postulate, added by hand. When does it happen? What counts as a measurement? Does it require a conscious observer? There are several fundamentally different answers to these questions, and each one represents a distinct interpretation of quantum mechanics. The Copenhagen interpretation. Collapse happens during measurement. What counts as measurement is not sharply defined, but this works in practice. Do not ask what happens between measurements. The question is meaningless. The many worlds interpretation, proposed by Hugh Everett in 1957. There is no collapse. The wave function never collapses. At every quantum event, the universe branches. Each possible outcome is realized in its own branch. All branches are real. The cat is both alive and dead, in different branches of reality. Decoherence. When a quantum system interacts with its environment, air molecules, thermal radiation, surrounding atoms, its superposition becomes entangled with an enormous number of degrees of freedom and becomes practically unobservable. This explains why we never see cats in superposition. But it does not explain why we perceive one definite outcome rather than all of them. Quantum Bayesianism, or cubism. The wave function is not a property of the object, but a description of the observer's beliefs. Collapse is just updating information.
Physics describes knowledge, not the world as it is. All of these interpretations produce identical experimental predictions. None of them can be chosen over the others on the basis of evidence. The debate continues. This is the honest picture. 100 years after the creation of quantum mechanics, no consensus on what it means. The measurement problem is an open question.
But while physicists debate it, quantum mechanics keeps making predictions and keeps being right. And one of its most beautiful and practically important results is a phenomenon that is responsible for the sun shining. In classical physics, a particle approaching a barrier can only get through if it has enough kinetic energy. Not enough energy, it bounces back, no exceptions. In quantum mechanics, it is different. The wave function of a particle does not cut off sharply at the edge of a barrier. It decays exponentially inside the barrier. If the barrier is thin enough, the wave function leaks through to the other side with a non-zero amplitude. That means there is a non-zero probability of finding the particle on the other side of the barrier, even if it does not have enough energy to quote-unquote climb over it. This is tunneling. The core of the Sun has a temperature of around 15 million degrees Kelvin, roughly 27 million degrees Fahrenheit.
At that temperature, protons are moving very fast by thermodynamic standards. But for nuclear fusion to occur, two protons have to get close enough for the strong nuclear force to grab them. And to do that, they have to get past the electrostatic barrier, two positive charges repelling each other. The calculations show that even at 15 million degrees Kelvin, protons are moving too slowly to overcome that barrier classically. By the classical picture, no fusion should be happening. The sun is shining. Fusion is happening. The reason? Protons tunnel through the Coulomb barrier. Their wave functions leak through it, and with some probability, two protons end up close enough for fusion to begin. Without quantum tunneling, stars would not burn. There would be no stellar nucleosynthesis, no heavy elements, no you. Transistors, the building blocks of modern electronics, also depend on quantum tunneling. In today's processors, transistors are only a few nanometers wide. At those scales, tunneling is not a side effect to be engineered around, but a core mechanism to be controlled. Managing the probability of an electron tunneling through a barrier by adjusting a voltage is essentially how a transistor switches. The scanning tunneling microscope lets us image individual atoms. A sharp metal tip scans the surface of a material without touching it. Electrons tunnel across the gap between the tip and the surface, a few angstroms of vacuum. The tunneling current drops exponentially with distance, which lets the instrument map the surface topology with atomic precision. The first images of individual atoms on a surface were made with a scanning tunneling microscope in the early 1980s. Quantum tunneling is not laboratory exotica, it is the physical mechanism behind things you use every day. Tunneling is quantum mechanics at its most practical.
But there is one other phenomenon that Einstein called spooky, and which has now become the most valuable resource in modern physics. After Aspect's experiments and the subsequent tests of Bell's inequalities, entanglement stopped being a matter of philosophical debate and became a measurable, reproducible fact. Entangled particles are particles whose quantum states are correlated in such a way that you cannot describe them individually. There is only a joint quantum state for the whole system. Measuring one instantly determines the state of the other, regardless of the distance between them. And it turned out this is a resource: quantum cryptography. If you transmit information using individual quantum particles, say photons with a specific polarization, it cannot be intercepted without leaving a trace. Any attempt to measure a photon in transit will alter its state and introduce detectable errors. The receiver sees the errors and knows someone was listening.
The security here is guaranteed not by mathematical complexity.
which in principle could be broken with enough computing power, but by the laws of physics. Quantum key distribution is already operating in real systems. Quantum computing. A classical bit is 0 or 1. A qubit, a quantum bit, can be in a superposition of 0 and 1 simultaneously. Entangled qubits. The state of a system with n qubits is described in a 2 to the n dimensional space. 10 qubits, 1024 states at once. 50 qubits, more than a quadrillion. Quantum algorithms use this structure to explore many possible answers in parallel. Peter Shor's algorithm from 1994 factors large numbers into primes in polynomial time. This is a direct threat to most current encryption systems, which rely on the computational difficulty of factoring.
Quantum simulators can model molecules and materials with a precision that classical computers cannot reach at the relevant scales, opening up possibilities for drug discovery and materials science. In 2019, Google announced that its 53-qubit Sycamore processor performed a specific computation in 200 seconds that would have taken the best classical supercomputer roughly 10,000 years. IBM disputed that estimate. The argument about the exact numbers continues. The direction of travel is obvious. Entanglement, which Einstein called spooky and considered proof that quantum mechanics was incomplete, has become the central resource of quantum technology. The questions he raised, from disagreement, from a desire to disprove, opened a path toward a field that will reshape computing, communication, and security. Einstein was wrong in his conclusions. He was absolutely right in his choice of questions. Quantum mechanics works.
It builds instruments and creates technology. But there is a place where it quietly admits defeat, where its laws run into another great theory and both go silent. That place is at the heart of black holes and in the first instant of the Big Bang. Quantum mechanics has a rival of equal stature. Einstein's general theory of relativity, completed in 1915, describes gravity, not as a force acting at a distance, but as the curvature of spacetime caused by mass and energy. Massive objects warp the fabric of spacetime. Other objects move along those warped paths, which is what we perceive as gravitational attraction. General relativity has been confirmed with extraordinary precision. The deflection of starlight around the Sun, measured in 1919, gravitational redshift, the slowing of time in a gravitational field, which is why GPS satellites require relativistic corrections, gravitational waves from merging black holes, detected by LIGO in 2015. Both theories, quantum mechanics and general relativity, are right. Both have been tested to the limits of our measuring ability. The problem is that they are fundamentally incompatible. Quantum mechanics describes the universe as discrete, probabilistic, governed by operator algebras and uncertainty principles. General relativity describes gravity as the smooth, deterministic curvature of a continuous spacetime. When physicists try to apply quantum methods to gravity, infinities appear. Not small discrepancies, genuine, unresolvable divergences. The theory breaks down. For most situations, this does not matter. Gravity is vanishingly weak at the scale of individual particles. The electromagnetic force between two protons is roughly 10 to the 36th times stronger than the gravitational force between them. At ordinary conditions, quantum corrections to gravity can be completely ignored. But there are two places in the universe where both theories are needed simultaneously. The center of a black hole. According to general relativity, gravitational collapse produces a singularity, a point of infinite density and curvature. What happens there is beyond the reach of classical theory. You need quantum gravity.
the first instant of the Big Bang, when all the observable universe was compressed to a scale smaller than what physicists call the Planck length, roughly 10 to the negative 35th meters, or about 4 times 10 to the negative 35th inches. At those scales, quantum fluctuations in space-time become significant. You need quantum gravity. In both cases, our best theories honestly say, we do not know. Candidates exist. The best known are string theory and loop quantum gravity. String theory proposes that elementary particles are not point objects, but tiny vibrating strings. Different modes of vibration correspond to different particles. The theory is mathematically beautiful, describes quantum gravity, and is internally consistent.
But it requires the existence of 6 or 7 extra spatial dimensions that have never been observed. And it has not yet produced a testable prediction that differs from standard theories. Loop quantum gravity proposes that space-time itself is quantized, not continuous but discrete, made of elementary volumes at the Planck scale. The smooth space-time we perceive is a macroscopic approximation. This theory also has not yet produced testable predictions. 125 years after Planck, we have no unified theory describing all 4 fundamental forces. The crack in the foundation is real, and it marks the most important unsolved problem in theoretical physics. Quantum mechanics goes silent at the event horizon of a black hole. But right at that boundary, where both theories need to apply and both break down, a discovery was made that connected quantum mechanics to the nature of information itself. 1974.
Stephen Hawking, 32 years old, applies quantum field theory to the space-time around a black hole. Classically, a black hole is a perfect absorber. Nothing escapes beyond the event horizon. No light, no matter, no information. Hawking found an exception. The energy-time form of the uncertainty principle means that even in a vacuum near the event horizon, virtual pairs of particle and antiparticle are constantly appearing and annihilating. Normally, they disappear immediately. Near the event horizon, a different fate is possible. One particle from a pair falls behind the horizon while the other escapes into space. The escaping particle carries real energy. To a distant observer, the black hole is emitting radiation. This is called Hawking radiation. Its temperature is inversely proportional to the mass of the black hole. For a black hole of stellar mass, the temperature is inconceivably small, far colder than the cosmic microwave background. Essentially impossible to measure.
But in principle, given enough time, a black hole loses mass through this radiation and eventually evaporates entirely. This creates a paradox. When you throw a book into a black hole, the information in that book, the specific arrangement of its atoms, its complete quantum history, disappears behind the event horizon. Hawking radiation is thermal. It is determined entirely by temperature and carries no information about what fell in. All black holes of the same mass emit identical Hawking radiation, regardless of whether what fell in was books or gold or nuclear weapons. When the black hole has fully evaporated, where did the information go? Was it destroyed? In quantum mechanics, information is never destroyed. This is a fundamental principle called unitarity. Quantum evolution is reversible. From any future state, you can reconstruct the past state. Information is always conserved. If black hole evaporation destroys information, quantum mechanics is violated.
If information is not destroyed, it somehow comes out of a black hole. From somewhere, nothing can escape. This is the black hole information paradox. Hawking long maintained that information was genuinely destroyed, and that quantum mechanics would need to be modified. In 2004, he changed his position, conceding that information is probably preserved,
but the mechanism by which it gets out remains actively debated. One of the more compelling ideas is the holographic principle. All the information in a volume of space can be encoded on its boundary surface, like a hologram. The information about the book is encoded on the event horizon and eventually leaks out with the Hawking radiation, in an extraordinarily scrambled, practically impossible to decode form. The information paradox connects quantum mechanics, thermodynamics, information theory, and gravity into a single open question. It is without a settled answer. The information paradox is an open question. While theorists work on it, quantum mechanics has found an unexpected ally in living things, in birds crossing continents, in leaves capturing sunlight. For a long time it was assumed that quantum effects only existed in cold, isolated, carefully shielded systems. A warm, wet, molecularly noisy biological environment should destroy any quantum superposition almost immediately through decoherence. Life is classical. Quantum mechanics is for laboratories. It turns out this is not quite right. Photosynthesis. When a photon is absorbed by a chlorophyll molecule, it creates an excitation called an exciton, an excited state that needs to reach the reaction center. The efficiency of this energy transfer in the first stage of photosynthesis is close to 95%. In 2007, Graham Fleming's group at Berkeley published an experiment using ultra-short laser pulses on photosystem molecules.
They detected quantum coherent oscillations. The energy appeared to be exploring multiple pathways simultaneously, something like a quantum superposition. Classical random walk models would not produce this level of efficiency. This result was disputed. Follow-up experiments in different groups gave mixed results. The question remains open, but it cannot be closed. Magnetic navigation in birds. Migratory birds, such as the European robin, can detect Earth's magnetic field with enough precision to navigate across continents. The leading hypothesis involves a molecule called cryptochrome in the bird's eyes. When a photon is absorbed, it creates a pair of radical molecules, molecules with unpaired electrons. The spins of those electrons are entangled. Earth's magnetic field influences how quickly this entangled pair evolves, altering the chemical reaction that follows. The bird perceives this as a signal, possibly as an overlay on its visual field, and uses it to navigate.
If this model is correct, a living bird uses quantum entanglement in its own eyes to sense a magnetic field. The spooky action that Einstein found unacceptable is what lets a robin cross an ocean. Experimental support for this hypothesis is real and growing, though full confirmation is still pending. Quantum tunneling in enzymes. In a number of enzymatic reactions, especially those involving the transfer of a proton or electron, the reaction rate at body temperature significantly exceeds what classical physics allows. Measurements of temperature-dependent reaction rates point to tunneling as a major contributing factor. The proton slips through the potential barrier rather than climbing over it classically. Life, it seems, does not merely exist within the quantum world. It uses the quantum world, superposition, entanglement, tunneling, for some of its most important processes. We are only beginning to understand this. Quantum biology opens up an unexpected picture. Life and quantum mechanics are not opposites, they are partners. But this brings us back to the central question of this whole story, the one that has been there from the beginning and still has no answer. Let us go back to where we started. 1927, Brussels, the most intelligent photograph ever taken. Einstein and Bohr over breakfast. What exactly were they unable to share? Not the mathematics. It was the same for both of them. not the experimental predictions. Those matched. They could not agree on this. What is reality? Bohr said, "Do not ask what is happening to the electron between measurements. The question has no physical meaning. The electron has no position before it is measured. Quantum mechanics is a theory of measurement outcomes, not a description of reality as it is." Einstein said, "Things have properties independent of whether anyone is observing them. The moon exists when no one is looking at it."
A theory that denies this is missing something important. Bell showed this was testable. Aspect and others ran the test. Einstein's position, definite values plus locality, is experimentally refuted. Bohr won. But Bohr winning does not mean everything is understood. The measurement problem remains unsolved. When exactly does the wave function collapse? What counts as a measurement? Is a conscious observer required? The Copenhagen interpretation says, "Do not ask." This is beyond physics. The many worlds interpretation says, "There is no collapse, the universe branches." Decoherence explains why we do not see cats in superposition, but does not explain why we see one definite outcome. Cubism says the wave function is an observer's information, not a feature of the world. Relational quantum mechanics says quantum states are relations between systems with no absolute reality. All these interpretations produce identical numbers. None can be chosen over the others on empirical grounds. The debate continues. This is a unique situation in the history of science. We have a theory, verified to unprecedented precision. Quantum electrodynamics predicts the magnetic moment of the electron to 12 decimal places of accuracy. No other theory in the history of physics has come close to that, and there is no fundamental agreement on what that theory is actually describing. Physicists joke about shutting up and calculating. That is, honestly, the position of most working specialists. The equations work, the predictions are right. Why worry about interpretation? That is pragmatic. It does not satisfy people who want to understand rather than just compute. Maybe those who say the question of, quote unquote, what is real between measurements is simply beyond physics are correct. Maybe physics answers questions about what instruments will measure, not what exists independently of measurement. Maybe the next great theory, quantum gravity, will clarify something. Produce new facts that allow us to choose between interpretations. Maybe the answer will come from where we are not expecting it, the way it usually does in physics. For now, the honest picture. We have mathematics that works, and no agreement on what underlies it. The cat is still in the box. The wave function collapses, or it does not. Reality is non-local, or it branches, or it is all just a language for describing measurements. Nobody knows. December of 1900, Berlin. Max Planck stands before an audience and announces that energy is discrete. He thinks this is a temporary fix that someone will soon replace with a proper explanation. 1905, Bern. A young clerk takes Planck's idea literally and explains the photoelectric effect. He adds to physics its first unavoidable paradox. Light is simultaneously a wave and a particle. 1912 and 1913, Manchester and Copenhagen. The atom turns out to be mostly empty and unstable by classical theory.
Bohr introduces rules that save it, without foundation, simply as postulates. 1923 and 1924, Paris. A prince asks, "What if the electron is also a wave?" He writes down a formula. 3 years later, it is confirmed experimentally. 1925 and 1926, Helgoland and Arosa. Two equations, one written on a rocky island during a hay fever attack, the other in an alpine chalet, turn out to be mathematically equivalent. Quantum mechanics is complete.
1927, Brussels. 17 current or future Nobel laureates are photographed together. Off camera, the daily ritual: trap, escape, new trap. Einstein loses every round. He does not give up. 1935, Princeton, the EPR paper, spooky action at a distance. Schrödinger coins the word entanglement. 1955, Princeton, Einstein dies, unpersuaded. 1964, Geneva, Bell turns philosophy into mathematics. 1982, Orsay, aspect turns mathematics into an experiment. Bell's inequality is violated. Einstein was wrong about hidden variables. Entanglement is real. 2022, Stockholm, the Nobel Prize for experiments with entangled photons. And here is the thing most worth noticing about all of this. Einstein raised the question of entanglement because it horrified him. He described it as evidence that quantum theory was incomplete. He wanted to show it could not be right. His own questions led directly to the experiments that proved him wrong. And those experiments then opened the path to quantum computing, quantum cryptography, and quantum sensing. Technologies that are changing the world right now. He was wrong in his conclusions. He was completely right in his choice of questions. Bohr won the argument, but he himself said that anyone who is not shocked by quantum mechanics has not understood it. 125 years after Planck, the cat is still in the box.
Nobody has agreed on what the wave function means. The crack between quantum mechanics and gravity has not been bridged. But the universe has not been waiting for us to agree. Right now, while you are listening to this, hundreds of trillions of neutrinos are passing through your body every second. Too faint to interact with anything, streaming through you as if you are not there. The light from your screen is arriving at your eyes not as a continuous wave, but as individual photons, one at a time, far too fast to distinguish. The atoms in your body have not collapsed into their nuclei, because the uncertainty principle will not allow electrons to be too precisely located anywhere near a nucleus. The transistors in the processor of whatever device is playing this are working because electrons tunnel through barriers they should classically never cross. All of this is happening right now, continuously, without your awareness of it. Planck discovered this in 1900 and did not believe his own discovery. Einstein took it seriously in 1905 and spent his last 30 years trying to prove it could not be true. Bohr defended it his whole life and died without convincing everyone. And the universe was running exactly this way the entire time. You are a temporary concentration of quantum fields that permeate all of space. Your atoms are governed by probabilities. Your device works on tunneling. The light you saw today arrived in quanta. The strangest part of any of this is not the facts themselves. The strangest part is that we found them out at all. That generations of people with pencils and chalkboards arguing by post across a continent managed to pull out the rules by which reality operates at its deepest level. Rules that look like nothing else in our experience. Rules whose meaning we still cannot fully agree on, but which work. Good night. People behind the equations. The quantum story is not only about formulas. It is about people who wrote them. And behind every name is a specific individual with a specific life that shaped how he thought about nature. Max Planck lived to 89 and outlasted nearly all of his children. His son Erwin was arrested in 1944 on suspicion of involvement in the plot against Hitler. Planck personally appealed to the Nazi leadership on his behalf. Irvin was executed in January of 1945. Planck survived him by only 2 years, dying in 1947. The man who discovered the quantum of action and wrote the equation that launched the 20th century in physics spent its final years in an occupied, devastated country, having lost everything he cared about. When you read his words about the act of desperation, about quantization as a forced step he himself did not want to take, there is something in the cadence of a person who had a lifelong habit of doing what was necessary rather than what he wanted. Einstein is often portrayed as a stubborn conservative who rejected quantum mechanics. This is unfair. He made enormous contributions to quantum theory himself, not only the photoelectric effect. In 1917, he described stimulated emission of radiation from atoms, the physics underlying lasers. In 1924 and 1925, working with Satyendra Nath Bose, he developed the statistical framework for particles with whole number spin, Bose-Einstein statistics, which predicted the Bose-Einstein condensate, finally observed experimentally in 1995. His disagreement with the Copenhagen interpretation was not ignorance.
It was a philosophical position. He believed physics should describe reality, not just the results of measurements. That is not an anti-scientific view. It is a realist position in the philosophy of science, one that many serious thinkers still hold. "When I am not working, I am thinking about quantum mechanics," he said in his later years. Not with pleasure, with unease. Niels Bohr was famous for never finishing a sentence. He would think out loud, begin one idea, shift to another, loop back. His lectures were difficult, his papers were harder. But this very slowness, this willingness to hold an unresolved thought open rather than rush to an answer, made him a great physicist. He had no interest in appearing to have the answer before he actually did. Pauli once wrote about him that Bohr did not think when he spoke. He thought by speaking, meaning that his thinking happened in the course of conversation, through dialogue, through objection, through the act of saying the thing out loud. This is why he found his way out of Einstein's breakfast traps. He found them in conversation, not at a desk. Heisenberg was not just young, he was free, in the way that someone without settled preconceptions about what a physical theory must look like can be free. He did not approach the problem thinking, quote, unquote, an equation should describe a trajectory, because it always has. He approached it thinking, let us start from what we can actually observe. That freshness is very hard to maintain into middle age. The hay fever that drove him to a rocky island with no pollen was, in a certain ironic sense, one of the conditions that produced quantum mechanics. Schrödinger was in exceptional form in December of 1925, emotionally, physically, intellectually. He was absorbed by de Broglie's problem. He had time. No departmental meetings, no obligations. The equation that describes the quantum behavior of everything we know about chemistry, atoms, semiconductors and superconductors, was written in a chalet in the Alps, under circumstances that his era considered irregular. History should maybe be less judgmental about the conditions under which good thinking happens. What superposition actually is, an honest attempt. The word superposition gets used often and almost always explained badly. Here is an honest attempt. In classical physics, an object is always in one definite state. A coin is heads or tails, a cat is alive or dead, an electron is here or there. In quantum mechanics, before measurement, an object can be in a superposition of states. An electron can be in a superposition of here and there. A photon can be in a superposition of vertically polarized and horizontally polarized. What does that mean? It does not mean the electron is quote-unquote in both places simultaneously in the familiar sense. You cannot set up two detectors and find the electron at both at once. When you measure, you always find it in exactly one place. It does not mean you simply do not know where it is. If that were the case, superposition would not produce interference. But it does. The interference pattern in the double-slit experiment is an experimental fact that is completely incompatible with the interpretation of mere ignorance. Superposition is a mathematical state in which a system is described by a linear combination of basis states. This combination has amplitudes, complex numbers that determine the probability of each outcome when you measure. But beyond that, those amplitudes can interfere with each other, reinforce or cancel, in ways that are impossible if all you mean is that you do not know. The best analogy is sound.
When two sound waves overlap, they interfere. In some places they reinforce. In others, they cancel. A superposition of two waves is not we do not know which wave is there. It is a real physical state that behaves differently from either wave alone. Quantum superposition is the same for probability amplitudes. A system in superposition is a system with real, measurable interference effects between states. When measurement happens, interference disappears. We get one result. But before measurement, the interference was real. And that is what distinguishes quantum superposition from ordinary ignorance. Quantum mechanics, as discussed throughout this script, describes systems with a fixed number of particles: 1 electron, 2 electrons, a hydrogen atom. But in the real world, particles are created and destroyed. A photon is absorbed by an electron, the photon vanishes, the electron moves to another energy level. A proton and antiproton collide. Both disappear, other particles appear. To describe those processes, you need quantum field theory. The idea: the fundamental objects are not particles but fields. An electron field, a photon field, quark fields. Fields defined at every point in space at every moment in time. Particles are excitations of fields. An electron is a localized excitation of the electron field. A photon is a localized excitation of the electromagnetic field. This changes the picture. The question, where is the electron, becomes, what excitation does the electron field have in this region of space? The vacuum, the lowest energy state of all fields, is not empty space. It is a state in which there are no particles, but the fields are not zero. Quantum fluctuations of the fields always exist, even in the vacuum. This is where virtual particles come from, where the Casimir effect comes from, where the Lamb shift comes from. Quantum field theory is the framework that unites quantum mechanics with the principles of special relativity. The standard model of particle physics is a specific quantum field theory describing all known particles and 3 of the 4 fundamental forces. It is quantum field theory that gives us 12 decimal places of precision for the magnetic moment of the electron. It is quantum field theory that produced the predictions confirmed at the Large Hadron Collider at CERN. And it is quantum field theory that breaks down when you try to include gravity. 1900. Planck introduces the quantum of action, explains thermal radiation. 1905. Einstein explains the photoelectric effect through photons, publishes the special theory of relativity. 1909 through 1911. Rutherford discovers the atomic nucleus. 1913. Bohr proposes the planetary model of the atom with quantized orbits. 1921. Nobel Prize to Einstein for the photoelectric effect. 1923. De Broglie proposes the wave nature of matter. 1925. Heisenberg creates matrix mechanics on Helgoland. 1926. Schrödinger publishes the wave equation. Born gives the probabilistic interpretation of the wave function. Schrödinger proves the equivalence of both approaches. 1927.
Heisenberg formulates the uncertainty principle. Davison and Germer confirm the wave nature of the electron. The Fifth Solvay Conference in Brussels. 1928. Dirac creates the relativistic equation for the electron, predicts antimatter. 1932. Anderson discovers the positron, confirming Dirac's prediction. 1935. The EPR paper. Schrödinger proposes the cat thought experiment, coins the word entanglement. 1947. The transistor is invented at Bell Labs. 1948. Quantum electrodynamics. Feynman, Schwinger, Tomonaga produces predictions of unprecedented accuracy. 1952. David Bohm independently develops the pilot wave interpretation of quantum mechanics. 1957. Hugh Everett proposes the many worlds interpretation. 1964. Bell publishes the inequalities separating quantum mechanics from hidden variable theories. 1972 through 1982. Experimental tests of Bell's inequalities by Clauser and Aspect. Result: quantum mechanics wins. 1981. Feynman proposes the concept of quantum computing. 1994. Shaw publishes the quantum factoring algorithm. 1995. Bose–Einstein condensate is observed experimentally, 70 years after the theoretical prediction. 1998. First experiments in quantum teleportation of states. 2007. First indications of quantum coherence in photosynthesis. 2015. LIGO detects gravitational waves from merging black holes. Loophole-free test of Bell's inequalities in Delft. 2019. Google announces quantum advantage with the Sycamore processor. 2022. Nobel Prize to Aspect, Clauser, and Zeilinger for entanglement experiments and verification of Bell inequality violations. The story is still being written. Conversations about quantum physics often sound like conversations about the distant particles, distant laboratories, distant abstractions. But all of this is here, right now, in the place where you are sitting or lying down. The atoms that make up your body, roughly 7 times 10 to the 27th of them, exist only because the uncertainty principle will not allow electrons to fall into the nucleus. Without quantum mechanics, there would be no stable atoms, no molecules, no you. The chemical bonds holding the DNA molecules in your cells together are a quantum phenomenon. The sharing of electrons between atoms that creates a covalent bond is described by quantum mechanics and has no classical explanation. The sunlight that gave energy to everything you have ever eaten is the product of nuclear fusion, which happens because protons tunnel through the Coulomb barrier. Vision is the result of photons being absorbed in the retina. Each photon is a quantum of the electromagnetic field. The absorption process is described by quantum electrodynamics. The transistors in your phone, your computer, in every electronic device, quantum devices. MRI scanners that allow doctors to see inside organs without surgery use the quantum spins of hydrogen nuclei. Lasers, in barcode readers, in surgery, in fiber optic communication, in measurement instruments, are a direct application of Einstein's theory of stimulated emission, worked out in 1917. Solar panels work on the photoelectric effect, discovered by Einstein in 1905. All of this is quantum mechanics in daily life. You do not see the quantum world. It is far too small. But you are made of it. You live in it. You use it every day. And the most remarkable thing is that people with pencils and chalkboards, writing letters across a continent, arguing at breakfast tables, worked out how it operates. Not knowing what they were opening, not knowing what the applications would be. just following the questions wherever they led. Planck was asking why hot objects glow the way they do. Einstein was asking why light knocks out electrons in that particular pattern. De Broglie was asking why not particles too. Every one of those questions sounded local, technical, almost boring to anyone who did not see what it would become. Every one of them changed the world. There is a temptation to end a conversation about quantum physics with some clean resolution, a formula of understanding, an explanation that puts everything in its place. There is none. And this may be exactly right. Quantum mechanics is the only fundamental physical theory in history whose foundations include irreducible uncertainty, not as a technical limitation that the next generation will overcome, but as a basic feature of reality. Before measurement, particles do not have definite properties. This is uncomfortable. Einstein could not live with it. Schrödinger invented his cat precisely because he could not accept the implications of his own equation. Planck thought quantization was a temporary workaround. But uncertainty is not a sign of ignorance. It is a form of honesty. A physics that said we know everything would be false. A physics that says, here is what we know, here is how precisely, here are the limits of its validity, and here is what we do not know. That is honest. Quantum mechanics is honest, to a sometimes uncomfortable degree.
To the point where it says, we predict measurement results with unprecedented precision, and we cannot tell you what is happening between measurements because there is no agreement, and the question may not even be well formed. This can feel like evasion, or it can feel, if you turn toward it from the right angle, like an invitation. Because open questions are not a weakness in a theory. They are the places where the story continues, where the next Planck, the next Bell, the next de Broglie will find a question that everyone thought was merely rhetorical, and discover in it the key to the next revolution. The quantum story did not end in Brussels in 1927. It did not end in Orsay in 1982. It did not end in Stockholm in 2022. It continues in laboratories, in theoretical papers,
in conversations between physicists who may be arguing over breakfast, just as Einstein and Bohr once did, about things that seem irresolvable. And from those arguments, something like understanding eventually grows. The universe is not in a hurry. It will wait. And in the meantime, neutrinos are streaming through you. Photons are arriving one by one. Electrons are tunneling. Entangled pairs are correlating across space. All of this right now. Without your permission, without waiting for your understanding. That is simply how things are.